Let's identify all the points of inflection. What's that? It's where the concavity changes. And determine the intervals where the function is concave up or concave down. So let's start by cheating, actually, and graphing it, which we can do without a graph. But I think it's going to be good to give us a visual. So 1/3 x cubed minus x, minus x. And we'll just go on the standard window. We'll go zoom 6. And we have, concave down, concave up. So here's what's going on. We have an interval where the function is concave down and an interval where the function is concave up. So let's just go ahead and talk about it. In this interval, the second derivative will be negative, and in this interval, the second derivative will be positive, okay? But we're getting ahead of ourselves. Let's find the second derivative. Oh, let's use black. F prime is x squared minus 1. F double prime is 2x. We need to know where the second derivative equals 0 or doesn't exist. This second derivative is always going to exist for all real numbers. So there we go, x equals 0. So the same stuff we did with the first derivative, we will now do with the second derivative. See, look familiar? Negative infinity and infinity, in that order, I guess. The negative values I plug into the second derivative give me 2 times the negative, which would give me, well, a negative. So the second derivative is negative. Plug in a positive, you get 2 times a positive, you still get a positive. So identify all points of inflection and determine the intervals where the function is concave up or concave down. Okay, well, actually, there's the graph. Aren't you glad you have that now? Now that we've graphed the whole thing, we'll look down there and we'll kind of use that as a visual as well. So here goes. At what x values do we have a change in concavity? Well, let's write our answer. Let's use green. So we have a point of inflection at x equals 0, and we have a graph that is concave down on the interval from negative infinity to 0, because that's where the second derivative is negative, down is negative, and we're going to have concave up from 0 to infinity. Now, things get a little tricky here. Using the same function as the previous problem, seen here in the graph, use the second derivative to determine if each critical point, whoa, pause, critical point? Critical point, those are maximums or minimums, right? If it corresponds to a maximum, minimum, or neither. Wait, now I have to find a critical point? So I need to go back to the first derivative and do something. Okay, no, whoa, wait a minute. I've already got the second derivative. Now I've got to go back to the first? Yeah, let's do it. Here goes. First derivative, we already found it, was x squared minus 1. We'll set that equal to 0, and x equals 1 or negative 1. So those are the critical values. Those are the x values that correspond to critical numbers. Now, let's just kind of look at this. Check this out for a second. X equals positive 1 is obviously right there, okay? X equals negative 1 is obviously right there. And we're just going to state some obvious things. And this is going to lead us somewhere. This is a relative minimum. No one is surprised that I pointed at that. Now, clearly it's not the minimum. It goes down forever. And this one is a relative max, and it does go up forever. But this is a relative max, this is a relative min. On this interval, right there, the second derivative is negative. That has been established. And the graph is therefore concave down. Follow me here. If I have a critical point with a concave down graph, I am looking at a maximum. If I have a critical point on an interval that is concave up, then I have a minimum. Let me say it again with a blank piece of paper. A man walks up to you and hands you this graph. That didn't mean to turn it down like that, okay? Concave down, right? Maximum, right? Right? Right. Okay, so we have a maximum. You're going to have a maximum when you have a critical point on an interval that's concave down. All right, follow me again. Here goes. Minimum, right? Minimum value, right down there at the bottom. That's my critical point. It's X value. Graph is concave up. So let's flip the paper over. Mine's on a separate piece. And let's do this thing. If the first derivative is equal to 0, okay, that's critical. Really, that's a critical point. The possibility of a critical point. And the second derivative is greater than 0, we have concave up. So let's finish this idea. What we really have is this situation right here. And this is C. That's what we're dealing with. Then C is the X value that corresponds, I'm trying to word it just right, corresponds to a minimum, relative minimum, okay, if the first derivative is equal to 0, all right? So we have the potential for a critical value. And the second derivative is negative, then we're in this situation right here. Concave down, we're going to have a C that is the X value that corresponds, I know it seems wordy, but I'm really trying to articulate things very clearly, corresponds to a maximum. And it's a little backwards from what you might think, because if we have concave down, it's a maximum, concave up is a minimum. It's a little bit backwards, but it works if you visualize it. And then if the first derivative is equal to 0 and the second derivative is equal to 0, then the second derivative test fails, meaning I am unable to determine maximum or minimumness.